And we are live. And I have chat open. And we'll wait a little bit until I see a couple of folks. Hey there. All right. I think we'll go ahead and start. Welcome, everyone, to MergePHP for December 2024. MergePHP is a collaboration of user groups to provide online virtual events that are PHP related. Hailing from Kansas City, Las Vegas, Vancouver, San Diego, Portland, Seattle, Phoenix, Austin, Boston, Atlanta, and Utah. If you are watching this stream live, you are at the right place at the right time. That is 7 p.m. Eastern, 6 Central, 5 Mountain, 4 Pacific, midnight Friday UTC. And yeah, we've been doing this since 2020, and thanks to all of the organizers who have pitched in to have a pretty consistent schedule of talks and such for MergePHP. Now, one thing that we do every month is if you have PHP Storm, then you can throw this JetBrains license at something else, WebStorm, IntelliJ, what have you. If you don't have PHP Storm yet, drop an email to chris@atlantaphp.org, and first one gets a 1-year license to a JetBrains product. So definitely worth checking that out if you do not have an active license for Storm or whichever other IntelliJ IDE you would like to use day to day. As always, we're taking a look here at current PHP support windows. If you are on 8.0, please upgrade. It is no longer supported unless your OS or Zend, if you're paying for that, is backporting fixes. 8.1 is still actively maintained for security fixes. However, you're not going to get other bug fixes going into that. 8.2 it still has active support, but not for much longer. 8.3 and 8.4 are being actively supported, with 8.4 released back on November 21st. If you were here last month, then you saw Tim Bond walking through the new features in PHP 8.4. So we have a number of conferences, most of which in this case are not in the US or even not in North America, but we have conferences coming up as soon as December 22nd if you want to take a flight over to Tokyo. There's Symphony Online, PHP UK, conference in Nagoya, which I believe is a brand new one, Confu in Montreal, which is a polyglot conference, Dutch PHP conference, which is back in person. I think this is the second year that they're back in person. PHP Day in Verona, Italy. PHP Tech in May. This is the third time that they've been back. And then I'm sure the schedule will fill in a bit here between May and September, but API Platform Conference has announced nice and early for them. So we are on various socials, depending on which social you'll get either more or less up-to-date information, depending on whether I remember to log into Twitter that day. We are at PHPC Social, like a lot of the PHP community on the Fediverse. So definitely check us out on 1, 2, or 3 of these socials. To answer the question about Discord, if you go to, let me make sure that I get the URL right. It's phpc.chat. That will link you to Discord. They also have an IRC bridge that sometimes works, and I believe have a matrix bridge that sometimes works. But kind of the source of record is Discord, and that is a chat for the general PHP community. So it's a lot more active than anything MergePHP related would ever be. So we'd recommend you go there. Now, as I navigate back over to my slides, next month we will have Mark Niebergall talking through bug squashing with TDD. I'll give you all a minute to read through that slide so I don't have to talk through it. And if you have a talk idea, obviously we have January covered, we have today covered, but mphp.io/speakers will get you a form for that. Also, you can give us a shout on socials if you would like to speak. If you don't have a full, say, 45-minute or hour talk, that's fine. We can potentially throw lightning talks in here or split a session with multiple presenters. The nice thing with an online format is there's a fair amount of flexibility there. And with that, I will hand this over to Eric Mann in just a moment. But first, I'm going to read his bio since I don't have that listed on the slide. So Eric is a web developer, technical leader, and polyglot with over a decade of experience working with companies and projects, big and small. He's been working with PHP through his entire career, both professionally and recreationally. Today, Eric focuses his time on helping developers get started with and level up their skills with their technology of choice. So I will now drop, let's see, add Eric, add his slides. And let's do this. And Eric, take it away.
All of the fancy tools and technologies today. Can everybody hear me all right?
Loud and clear.
Perfect. Fantastic. So today we're going to talk a little bit about PHP and AI. AI is one of the bigger buzzwords today, and this is a talk that I've really been excited to give for quite some time. I was actually supposed to present about this at PHP Tech earlier this year and was unable to due to some family obligations. I was also supposed to present this at Cascadia PHP not that long ago and came down with some variant of the plague, apparently, and just could not breathe, could not speak, and could barely get through a conversation. So I'm happy to be here today. MergePHP, you get to be the first group to actually see this new and revamped talk about the intersection of PHP and AI, also known as the battle of the acronyms that don't mean much because they're both backronyms. PHP obviously is what we know and love, and AI is not actually intelligence, even though we talk about artificial intelligence all the time. And I'm going to explain a little bit about what exactly I mean by that. And to do so, first I'm going to talk about not AI, but machine learning, which is a much broader concept similar to AI, and some folks will use it interchangeably. I've been known to do that in the past. A lot of folks will refer to AI ML, so AI and machine learning, as if they're two different yet the same things. And it's important to understand exactly what we mean when we say machine learning, because obviously machines are not humans. They don't learn the way humans do. So we've come up with a bunch of clever abstractions to make machines mimic biological processes. So it looks like they learn. It looks like they're intelligent. It's a way that we try to make computers pretend to be fleshy. And whenever you think about that, just remember when we're dealing with computers, it's kind of black magic, but it's not at the same time. So remember, computers are computers. We can make them act similar to biological entities, but they are not biological. So we have to take shortcuts. I love this tweet or Zeet or whatever you call it these days with the newly named X about just remember when you're writing code, a CPU is just a rock that we tricked into thinking after we trapped lightning inside of it. So that just makes everything we do seem that much more magical. And I know it impresses my kids, so they think that daddy can do magic as well. But it's important to understand computers are deterministic. They don't do things at random. Life, biological processes, the neurons in our brains, everything that we do is biological, is random, and uses strong sources of randomness to actually be unpredictable. It's one of the reasons why you can never predict what your colleagues will do, what your children will do, what other people around you will do, or even what your dog will do if you give them certain things, because we have to train certain behaviors because there's so much randomness, and computers work best when they're not random. A computer that is random is useless, is a waste of time. They need to be deterministic. So we have to use hacks specifically with these computers to make them work as if they're biological entities. So one of the first hacks that we're going to talk about is the idea of genetic algorithms. This is something I was introduced to a long time ago at a real-time communication conference to illustrate how different .NET frameworks could leverage real-time communication in very fast ways, low latency, low bandwidth ways to communicate between different processes, but it allowed you to have these novel implementations that could mimic biological systems because of the low latency communication between different elements. So not going to talk too much about that demo specifically. Instead, we're going to do a different demo and talk about what a genetic algorithm is. Because again, this is a way that we can take a computer and we can build something into the computer to make it act like a biological, non-deterministic system. So a genetic algorithm is effectively creating a population of entities, just like if you're breeding flowers or breeding dogs or breeding animals, you're going to start with an initial population and they're going to be somewhat random. So much distribution, so much diversity between the different members of that population. They're not all alike, but you're trying to evolve the population to get to a specific goal, to go to a specific location. So we start with the initial population, and then we evaluate the fitness of each member of that population. So let's say you're breeding apples. You'll have different apple trees, each produce a different fruit. You're going to evaluate the fitness of each apple that's produced. Are the trees producing apples that are sufficiently sweet, sufficiently tangy, sufficiently crisp, the right color? Are they red? Are they yellow? Are they green? And you're going to evaluate the fitness of the apple trees based on how close they are to what you want them to be producing. From there, you're going to allow the members of the population who have the highest fitness to reproduce and create the next generation. And then to add some randomness in there, you're going to have mutations. In the real world, again, breeding apples or breeding dogs or breeding horses, you're going to have natural mutation that happens just because of the biological process. With genetic algorithms in a computer, we have to mimic this. We have to fake this by going in and changing the digital genome so it's mutated a little bit. And this allows us to avoid what's known as a local maxima or local minima. So in computer sciencey, AI type talk and mathematics, you might be looking at a curve. It's a bumpy curve. It has a bunch of bumps on it. It has a bunch of lines. You're trying to find the maximum point on the curve. To identify if you found the maximum point, you have to introduce these small perturbations, this amount of randomness with the mutation, to avoid getting stuck at a bump that might be higher than the points really close to it, but is not the maximum. So mutation gives us that additional randomness and allows us to push things forward to the next generation. Once we have that next generation, that next population, we go through the cycle again. Evaluate the fitness of each member, take the highest fitness members of the population, allow them to reproduce, add a little bit of token mutation in there as well, and then iterate and iterate and iterate until we get to our goal. In the physical world, the biological world, this is what researchers in Washington did to create the cosmic crisp apple, which is one of my favorite apples. It's actually a hybrid based off of Honeycrisp. So it has the sweetness of Honeycrisp, but it's got a much crunchier mouthfeel. So they gave us the crunchy of Red Delicious with the sweetness of a Honeycrisp apple through this kind of selective breeding and mutation and carrying on with apples. Now, in that illustration I mentioned before from that earlier conference I went to, the idea was, could we use a computer to simulate the million monkey problem? For those who are unaware of the million monkey problem, is the idea of if you have a million monkeys bashing around on the keys and on a million typewriters, how long will it take before they eventually produce the works of Shakespeare? Now, in the real world, it's very messy to give a bunch of monkeys typewriters. And if you give this talk in certain places where people are trying to translate in real time from English to the language of the place where you're presenting, you have to slow down here and explain we're not talking about actually creating warehouses full of monkeys. Otherwise, somebody will have to run on stage and interrupt so that people don't get mad at you. I'm talking about digital monkeys. Let's create digital monkeys in a computer, digital analogs of monkeys, and allow them to type on digital typewriters to see how long it's going to take for us to produce the works of Shakespeare. This is a novel implementation of a genetic algorithm. It's kind of trivial. It's kind of a toy implementation, but it does help illustrate what genetic algorithms can do. So just to, again, reiterate what the process is going to look like, we're going to start with an initial population. Since we're talking about writing Shakespeare, we're going to be talking about strings. So our population is going to be a collection of entirely random strings of bytes. And they're all going to be the same length as some target text that we're trying to achieve. In this case, to be or not to be, that is the question. Once we have all of these random strings, we're going to evaluate the fitness. And for this use case, we're going to measure the Levenstein distance between the string, the random string, and the target text. So how similar is it? How close is it? How many characters would you have to change, and by how much to actually get to the target text? We'll then take our high fitness members of the population and allow them to, at random, create a somewhat less random child generation with a little bit of mutation mixed in. So we'll have some children in this population. We're going to introduce randomness by incrementing a specific character up or down in the ASCII chart, just to avoid hitting a local maxima. This is where we get to bring in our demo. So now I'm going to pull over this console window. And over on the left-hand side, you can see I'm running a script called run.php. And I'm running specifically genetic monkeys on run.php. Now let's see what happens when we run it. Again, it's breeding lots and lots of monkeys to try to type. To be or not to be, that is the question. It took roughly 1,547 generations of, I was doing 200 monkeys per generation. So 200 monkeys at a time, breeding for 1,500 generations in order to get one monkey that could type to be or not to be, that is the question, by hitting keys at random. So once again, somewhat a trivial, kind of like a throwaway play illustration. The code is really fun to walk through, and it's all open source on GitHub if you want to take a look at it. But just again, to reiterate what we've done with our genetic algorithm, we created the initial population of 200 random monkeys. Each of these random monkeys was really just a completely random byte string that was the exact same length as our target text. We then evaluated the fitness for each string, allowed them to reproduce by taking two strings at random that were rated as high fitness and splicing them together, taking characters at random from each of the two strings and putting them together, similar to the way that genetic mutation works in the real world. And at random, we would introduce a little bit of randomness to some children to avoid getting stuck at a local maxima, so we could actually optimize things and get to where we needed to go. It worked. It was a very short string. It worked pretty fast. I used a super short string for the sake of the presentation, just to make it so that this wouldn't take forever for this to actually run. This demo was done entirely in PHP. You can also do it in JavaScript. I've done this successfully using web workers in JavaScript. And the demo that I mentioned earlier was originally written in C# using the Signal R library so that you could do this in ASP.NET. So there are lots of implementations. If you're writing in Go or possibly even Franken PHP, you can definitely use Go routines and do stuff under the hood as well. But in PHP, it works remarkably fast and is really fun. But genetic algorithms aren't limited to just throwaway texts. With Shakespeare and with virtual monkeys, there are a lot of other things you can do with them. Another option we have is the traveling salesman problem. If you haven't heard of the traveling salesman problem, the idea is you have a salesman who has to visit a certain number of cities. They have to visit each city each one time before they go home. We know exactly how far apart each city is, and we assume it's the same distance in either direction. The reason why we have to make that assumption is because in reality, you might have different roads that go different ways. You might have one-way roads. You might have a highway that only goes in one direction and a smaller surface road that goes in the other direction. So it might take longer to get from point A to point B than it takes to get from point B to point A. But we're going to throw that away for now and just assume the distance between each city is the same. And the objective is to minimize the total distance that the salesman travels on their trip. When you talk through it, it sounds like it should be fairly easy because you might think about, okay, I've got 4 or 5 cities I need to go through. I'm just going to plot them in a circle, make sure that I'm going the minimum distance possible. But in reality, cities aren't necessarily laid out very well. So in this case, you can see this illustration has cities at random. You might not know exactly which is going to be the optimal route that you want to take. So what we can do with our genetic algorithms is actually walk through and assign each city a letter, a character. And just like we did with Shakespeare, we can create a random population, we can put them all together, and then we can ask the computer to use a genetic algorithm to iterate as many generations as possible, as many generations are required in order to find the minima. What is the minimum distance you need to go? This is a much more practical problem than the genetic algorithm solving Shakespeare, because this is something you might actually do for traveling to different tour venues, maybe sports venues if you're going on a road trip, traveling to different companies if you're doing a sales presentation, just like the traveling salesman would. There are a lot of other applications as well that we'll discuss in a moment. But the idea here is that this is something that can be solved by, or at least approximated by, genetic algorithms pretty effectively. So let's look at what that will look like. So here you have an illustration, and this has 50 points on this grid. These are 50 points that were selected at random by a PHP application, and they represent cities. So assume you have a traveling salesman who needs to move through 50 cities. They're random cities and random locations, and the salesman needs to identify what is the most optimum path, what is the shortest amount of time he or she needs to travel to get through all of those cities. And the way we're going to do that is, again, I'm going to pull this console window over here for a second, but then we're not going to watch it because it's going to solve it directly on the browser instead. But the same run PHP command, there are several options in this console tool. One is cities to create a random list of cities, but now we're going to run the genetic algorithm against the traveling salesman problem. So I'll pull that back off to the side, and we will run it. And you can see as it's running, it's dynamically drawing the map of what it's going to look like, what the salesman is going to do. And it's doing, again, multiple generations as it's pushing forward, trying to find the optimum path that salesman can do, and it's done things entirely at random. In this case, we started with an initial fitness of 459. Let's just say that's miles, just for the sake of argument. So the initial fitness of the best random, just like picking the plot at random, would have been a 459-mile trip. After the genetic algorithm has run for 2,500 generations, the best fitness we've gotten to is about 200 miles. And you can see, just because you're all smart, you're all human, and you probably do this kind of plotting and everything when you're traveling as well, you can actually see that there are some shortcuts that could have been taken. The algorithm wasn't exactly perfect, but again, this is effectively a million monkeys hitting a million typewriters trying to plan your summer vacation to make it so that you're traveling the least amount of distance possible as you're actually traveling. I called it a broken demo for a reason, because you can see that demo took a while. It still wasn't optimal. To actually find an optimal solution, we would be sitting here probably for a couple of hours using a genetic algorithm. So once again, here was the use case that we were actually walking through. Just to remind you, the salesman must travel to all cities at least once before returning home. The distance between each city is fixed, and it's the same in either direction, and the objective is to minimize the total distance traveled. Genetic algorithms were one way to solve this problem, but there are plenty of other biological and physical analogs that we can use to identify what is going on and like how we can actually optimize this and move on. So what I'm going to talk through now is called an ant colony optimization. I can't do a show of hands to ask who's had to deal with ants in their kitchen or who's actually seen ants in the wild. Sometimes when you're walking down the sidewalk, you might see just a clump of ants on the sidewalk. They might be red, they might be black, could be some other shade in between. You might have two clumps of ants that are attacking each other, but when you see ants in the wild, you typically only see one or two, unless they're in a cluster. Unless you left your Halloween candy out on the counter, then you might see a lot of ants, and they're going to be in a nice line. And that line is going to be the shortest distance from their nest to the candy. But they didn't find it by saying, oh, there's candy on that counter, I'm going to go over to it. They use their own internal algorithms to actually solve this. The ants, the worker ants, actually go out at random looking for food sources. And when they find it, they can communicate with other ants to help optimize the most ideal path between point A and point B. If that sounds familiar, that's exactly what we need to do for the traveling salesman problem. So we'll use the same way ants solve problems to actually solve the traveling salesman problem as well. So with an ant colony optimization, you start with an ant, dropping them on a random city. You're then going to have the ant determine where it's going to go based on the attractiveness of the next destination. So in this case, the ant has an atlas. They can see all of the different cities that they need to travel to, and they can identify which one is going to be the most ideal or the most attractive. And it does this by identifying things like how far apart are they, where they're looking at, but they also will drop pheromones as they travel from one city to another. So the first ant is going to be looking at the world at random. There's not going to be any pheromone trail. It's just going to pick cities at random and move on. The second ant is going to look at all of the cities, and it's going to see the different paths between cities. It's not just going to see the cities, it's going to see the paths between them. And each path is going to have a different amount of pheromone deposited on it. As the ant travels, it drops more pheromone, and you're going to start having the pheromones build up and build up over time. As you go through the entire simulation, you will evaporate the pheromones as you go, and then repeat with more ants. And you keep going, and you keep going, and you keep going. And eventually what you're going to have is a sequence that looks something like this illustration I borrowed from Wikipedia. The first image on the far left is one example of an ant traversing through multiple cities on a map. The second map is showing where the pheromone trails are, showing all of the different connections that the ants have made. After you end up evaporating some of the pheromone, compounding some of the pheromone, you end up extracting what is going to be the most ideal case, which is what's happening in image number 3. And by image number 4, you now have an optimized pathing between all of the different cities that are in the map. Just like genetic algorithms, this is something that starts with randomness and is using a random number generator to keep things fair, keep things balanced, and keep things moving through. But it's also something we can do pretty effectively in PHP. So let's walk through a demo of this one as well. So we're going to come back to our traveling salesman problem. Just going to refresh the page. So we have the same 50 cities, the same points, the same layout, but this time we're not going to use the genetic algorithm. I'm going to bring my console screen over here. In this case, we're going to run the ant colony optimization. Now everybody pay attention. This is going to go pretty fast. I used 50 cities. I normally do it with fewer, but there we go. We're done. 2,500 generations was significantly faster than the genetic algorithm that we used before. And it ended with a final fitness of 124 miles. Remember, the genetic algorithm started with 450 miles, boiled it down to 200 miles, and the ant colony optimization boiled it down to 124. You can also see there are still a few minor optimizations that we might make as a human, where you come through and this leg down here might be a little bit redundant. The ants didn't quite figure this out just because of the pathing here. There might also be something we can do here with the way that these points are all connected together. But the ant colony optimization gave a very practical estimation of what the ideal path could be for traveling through these different 50 cities. We can also do this with a different one. So we've done it now with one set of 50 cities. If I come in here, this is the advantage of building console apps. I can come in here and set, I'll do 43 cities just to show that it's not an even number that makes a difference. And if we refresh the screen, we now have a different 43 cities than we had before. And if I rerun the traveling salesman problem with the ant colony optimization, it will give us a different pathing. Now, we can also look at this and see, just to demonstrate the fact that it's random, here was the initial run with 43 cities. Here's a new run with the exact same points, the exact same cities, and we can run it again because it's meant to be non-deterministic, or at least somewhat non-deterministic, as we're mimicking the biological scenario. You can actually see the difference. Well, there isn't much of a difference. It came up with the exact same solution for both. So it's getting close to what the actual solution should be. The trick is, with the traveling salesman problem, it's actually very difficult to solve with a computer. Some of the largest traveling salesman problems have taken supercomputers weeks to solve, and they don't scale much beyond a handful of cities. My simulation here only expands up to 56 cities, or 52 cities, and that's because I'm literally using A through Z, both lowercase and uppercase, so that we can leverage the million monkeys for the genetic algorithm. But real world applications might deal with thousands of cities, tens of thousands of cities. And when you start hitting those, that number, finding a correct solution, the final answer, becomes nearly unobtainable for modern computers. So that's why we need to use approximations, and both genetic algorithms and ant colony optimization are valid approximations for what the actual solution should be. So let's walk through just one more time what we did with the ant colonies and why they're valuable. Because we talked about cities. You might not be dealing with a traveling salesman moving between cities. You might be building computer peripherals, and you need to deliver them from one location to another. So ant colony optimization can be used to optimize vehicle routing. It can be used to optimize job ordering when you're actually dealing with things within a computer system to order different jobs so you know how to sequence them properly. If you're packing things together, whether it's packing things virtually or packing things in your suitcase, ant colony optimization can help solve the knapsack problem to identify the most ideal pattern in which you pack your knapsack. It can also be used in electronics design. It can be used in antenna optimization. It can be used in image processing. It can be used in network routing, specifically between different load balancers or in a very distributed computational environment. And it can also be used with protein folding and solving different problems in biomedical space. Nanoelectronic design is one that I kind of gloss over here, but it's one that I find just absolutely fascinating because it's the easiest way to actually see how these kinds of solutions can be very, very valuable. So for example, let's say you are building a computer. You need to build a circuit board for that computer, and you need to have a CNC machine drill holes in specific locations on the board in order for you to mount chips. If you have 5 holes, it is pretty trivial. Just drill the 5 holes and move on. If you have 100 holes, 500 holes, 1,000 holes that need to be drilled in this board, it becomes a planning problem because it's going to be very, very slow to drill them all in series. They might not exactly be in series. It's also infeasible to correctly, completely solve for what is the most ideal solution for plotting the CNC router to identify in which order to drill those holes. So you can use solutions like the ant colony optimization to identify an approximation for what it's going to look like. For example, once again, looking at this pattern, this might be the pathing for a CNC router to drill 43 holes in a motherboard to mount a bunch of chips. I mean, obviously it's not, but it could be. And if you can use a tool like ant colony optimization to shave 5% off your total time of manufacture for a specific chip or board or a component, you can now ship that much faster because you can produce that many more units in a fixed amount of time. And this is where things like genetic algorithms and colony optimization, there's also a solver called Concord, which is a commercial solver that people actually use in industry to solve this kind of problem in a similar pattern. But let's talk about some specific tools that you can use today. So you don't have to sit there writing your own ant colony optimization, your own genetic algorithm, building your own tensor processing units, even understanding what the different underlying frameworks are. There are tools that you can use today to leverage AI, leverage machine learning, and continue pushing things forward in your PHP applications. If you're working a lot with text, one of the things that takes a lot of time is properly categorizing that text or extracting keywords, extracting summaries, and identifying what is the value of this text that I have. What is the value of the text snippet? There are tools like Amazon Recognition that allows you to go through and identify what actually are the keywords. They will pull the keywords out of the text for you. Sorry, not Amazon Recognition, Amazon Comprehend. We'll go through. It's an AWS tool. It's available today. Anybody with an AWS account can use it. AWS Comprehend allows you to extract these keywords, extract topics, and pull everything together without hiring an intern or hiring somebody to go through and manually highlight what is it we're talking about. If you've got photography set up, you can use Amazon Recognition to extract labels from the photo. So Amazon Recognition will look at the photograph and then tell you, there's a person in the photo, it's outdoors, there's a mountain bike, there's a rock. One of my favorite XKCD comics is a product manager asking an engineer, I need a tool that can identify if this photo was taken at day or at night. Engineer says, great, it'll take me a week. Okay, and now I need to know whether or not there's a bird in the photo. All right, it'll take me 3 data scientists and 2 years. I'll get back to you when we get closer. You don't need to do that anymore. Amazon Recognition exists today, can pull all of this information out for you automatically. You don't have to do anything. Just give it the image. It's already pre-trained. It will give you out the labels. It will give you its confidence in those labels, in those elements actually being there, in those entities being present. You can also use it for text extraction or optical character recognition for text to actually convert things. And there are many other things it can be used for as well. Anybody who works in the WordPress space also has the advantage of fun tools like Classify. Classify is a plugin by the WordPress agency 10up, and it integrates with almost all of the different AI ML providers that are out there today. Everything from Google's Gemini to Microsoft Azure Machine Learning, OpenAI, ChatGPT, IBM Watson, Amazon Poly, and it's a fantastic way to start adding categorization to a WordPress system which is, again, is in PHP, without you having to say, okay, I'm going to go down into Python, I'm going to train my own models, I'm going to hire a couple of folks with PhDs and build this myself. You can leverage this today. The plugin itself is free. You just have to provide the platform access. So you have to have an OpenAI account, an IBM account, an Amazon account, an Azure account, or a Google Gemini account. And you provide that information to the plugin, and it will use those services and those tools for you to enrich your WordPress environment. So for example, you have a blog post where you start talking about what you want to talk about, but you don't want to take the time to fill out the tags, fill out the keywords. You just want to have it do it automatically for you. Classify will automatically generate categories for you, will generate keywords for you, and everything will move forward. It also works on legacy content, so you can have articles that don't necessarily have any tags, any categories, concepts, and you can click a button and classify, and they're generated automatically for you. So anybody who's using WordPress today can leverage these tools. Anybody who's not using WordPress but is still leveraging PHP, the WordPress plugin is open source and gives you a really great, proven in the market pattern that you can follow for integrating similar levels of platform communication into your own PHP application. Classify, like I said, is open source. It also has additional features depending on which platform you integrate with. So I recommend you leverage as many as you can. IBM Watson has a free tier. Azure Machine Learning has a free tier. AWS Support has a free tier. And you can do everything from image descriptions to smart crop, image tagging, and anything you need to do. Yes, the use of some of the models, to answer your question, Stefano just posted in chat, the usage of some of these models are free. The usage of the platforms are free, or some of them are free. Just like any other tool like this, you pay for consumption. So double check what the pricing is in your region for how much consumption there is. But most of these platforms offer a free tier. So you can get started for free, build your prototypes for free, and actually push things forward for free. And for an example of that as well, a tool that I built myself just to experiment with PHP and machine learning is a tool I call Clyden. Clyden was a tool that came out of my own job search where I got tired of writing cover letters for every job application I filled out because the recruiters were using AI to read my cover letters and just dismiss me. So I leveraged AI myself to write the cover letters for me. So Clyden will go through and it would read my resume and it would read the job description and then automatically give me a draft of a cover letter. And I say draft. I said draft a lot of times, or a candidate or approximation a lot of times. AI, again, is not intelligence. We talk about it being intelligent. It's not intelligence. AI is a computer approximation of biological process. So the ant colony optimization is mimicking what ants would do. The genetic algorithms is mimicking what genetic reproduction looks like. Text generators like LLMs, like ChatGPT, are mimicking what people would type, but they are first order approximations. Consider it like you paid somebody on Fiverr, you paid them $5 to write a quick first draft after they skimmed your resume. You're not going to immediately turn that in a job application. You're going to use Clyden to create a first draft, and then you're going to go through and revise it, polish it, put it in a template, and send it on, just like you would look at the ant colony optimization output of the traveling salesman problem, make a couple of hand modifications to further optimize it yourself, and then push it forward. AI and ML get you part of the way there. It does not get you all of the way there. It is not true intelligence. You still have to use your brain. You still have to use your intelligence to actually get it the rest of the way there. But the computer can automate most of the mundane components and get you most of the way there. Clyden is also pretty cool at just generating random text, like asking it to tell me what a talk proposal should look like for an upcoming conference. And I can neither confirm nor deny that I actually used that to prepare for this talk myself. Now, the cool thing about AI is that it's not the nefarious future that everybody keeps telling us it is. We're not building Skynet. We're not talking about, we're not talking about Skynet. There are people out there who would love to build Skynet, but I can tell you, having worked with AI and machine learning for several years, we are generations away from being anywhere near that level of technology. At the same time, AI itself, because it can mimic natural systems, can be used to automate many of the things that are difficult to automate because it can detect underlying patterns that might be non-obvious. It can find some optimizations that a human might miss when they're looking at the system because they're not looking at it the same way. But again, it just gets us part of the way there. It doesn't get us all of the way there. And it still requires human intervention, human supervision, and human finesse to get it across the finish line. And once again, with PHP, you can use all of these technologies. I showed you demos of both genetic algorithms and ant colony optimizations that were built entirely in PHP. WordPress has integrations demonstrating how you can use all of the different major platforms with PHP. The Clyden app that I mentioned before, Clyden.ai, you can use it today. It's available to anybody on the open internet, and it is a Laravel application. Everything is built entirely in PHP. Again, leveraging one of the largest LLM providers to do text generation that's out there. So it's possible. It's the future. It's not as scary as Skynet, even though Terminator 2 remains one of my favorite movies, but it's something that you can actually use today, leverage today, and push things forward today. So thank you very much. If anybody has any questions, Hal will not answer them, but I will try to answer them myself. Feel free to drop them in the chat. Stefano, yes, you would be locked in with some of the other providers. The advantage or the thing that you're going to want to do is make sure that you're abstracting as much as possible when you're dealing with this. So in PHP world, creating a provider class that wraps different levels of technology, and then also trying to experiment with, try to use AWS's image recognition software, and then try to use Azure's image recognition software. The other advantage of these different providers is they don't communicate a lot with each other. So you're going to have different levels of performance out of the models that they built and that they're providing on their platforms. So for depending on your level of photography, let's say you're trying to do entity recognition from images, IBM Watson might give you better results than Amazon, which might give you better results than Azure. So experimenting with all of the different providers is going to give you a sense of how they're processing the imagery and how they're actually tokenizing things and providing entities back to you. And if you can abstract this away by building things into provider classes or different classes within your application, it's going to make it much easier for you to, let's say you're selling a solution, turn on Amazon for one customer, Azure for a different customer, Google Gemini for a third customer, and so on. I'm looking in the chat to see if there are any other questions. Feel free to shout out and let me know. All right. Well, thank you, everyone. My slides are up on Speaker Deck. Like I said, Clyden.ai is available. It's a website. Anybody can use that. My code is also available on GitHub, and I am on Mastodon on tecton.network. Feel free to hit me up there if you have any further questions you didn't want to ask during the chat. Okay, so is this output of those APIs somewhat similar? Is there ever going to be a standard interface? No, they're not. They're not somewhat similar. The advantage is they typically return some sort of a JSON format. So that's where providing the abstraction, you can have basically one parser for AWS, one parser for Azure, one parser for Gemini, one parser for ChatGPT, but they're not super similar. So this is also why I showed the Classify plugin for WordPress, because it actually has this on the back end where they build abstractions around the different providers. So you can actually choose between, do I want Azure's image recognition? Do I want Amazon's image recognition? Do I want Google's image recognition? And they will provide a different, effectively a buffer class, depending on which option you select, to normalize the API output so that the rest of the application doesn't care what platform you're using. And that's the same approach I would recommend for anybody else who's trying to roll this on their own. All right. If there are no other questions, Chris, I think I'm turning it over to you at this point.
Okay. Yeah, I was just going to do final call for questions, but I think it's like the chat window is slowed, so I think we're good. Thank you so much, Eric. It was a really interesting discussion, presentation, and great demo of the tooling and stuff too. So thank you so much. We appreciate your time and coming out for us.
Thank you as well. And thank you everybody else for coming out today. And I hope you have a great afternoon. And for anybody I don't see in person between now and then, Merry Christmas and Happy New Year.
Thanks, you too. Mark, did you want to, well, no, I guess you talked to last, we had a slide about your upcoming presentation next month. So we don't have to, unless you want to talk more about it, we can wrap it up. Let's see. Oh, you're shaking your head. Yeah, I see Mark in the backstage zone here, shaking his head. No, thanks. I think we're good. Well, like I said, we have Mark presenting on TDD next month, and so we'll hope to see everybody then. Thank you all for coming this evening, and we'll see you next time. Thanks, y'all.